Let's try to solve these two problems using the square root decomposition technique. There is no extra logic here, just how to pre-process and how to query using this technique. We're going to resolve the static range sum queries and range XR queries. As we have seen in the previous videos, we can use the technique or the approach, the prefix sum approach, that take big O(n) as for the pre-process, and O or big O1 for the time complexity of one query, and O(n) extra space complexity. This is the best approach, I think, if we have a static range sum queries. But here we're going to practice on this square root decomposition technique in order to understand more how to pre-process and how to query using this technique. Let's see the first problem. As we have seen, we have an array of integers, and we want to query from, we want to compute the sum from an index A to an index B. By using the square root decomposition technique, we have our original array here, and we're going to build another array to be processed. Let's call it B, of size the ceiling of the square root of the size of the original array. For this example, we have n equal to 8, so square root of 8, the ceiling of square root of 8 is equal to 3, so our array is of size 3, blocks array. In this array, we're going to store every 3 cells in a cell and another array, the array B. So here we're going to store 9 for a 3 plus 2 plus 4, and these 3 cells in this block, and the remaining cells in this block. In order, if we want to perform a query, for example, let's take from 1 to 8, which means from 0 to 7, from here to here. As you see, instead of iterating over all the cells, we start from here, from 0, the left boundary, and as you see, we are at the beginning of this block, and we can use all this block to compute the sum. The entire block we can use it here because we are not reaching 7 here, so we have 9, and we jump here. We can see if we can use this block. Yes, we are at the beginning, and we can use the entire block here because 5 is less than 7. So we can use this value 7 and the next array. And we jump here, and we can use this entire block here, plus, which is 24, which is the answer. This is the main idea of the square root decomposition, as I have explained in the previous video. Let's try to code it. Of course, as I have said, we're going to use the square root decomposition technique. The time complexity of one query is or big O square root of n, which where n is the size of the original array. The whole code is the q times big O squared T of n, where q is the number of query. We need an extra space of big O square root of n. First, we're going to read the inputs, and now we're going to preprocess. First, I will build the original or the array of blocks. Let's compute the size first of the array of blocks, which is, as we have seen, the ceiling of the square root of n, and let's build the array of square root decomposition technique, which is integer or long. Let's take it long here. Let's call it b is equal. I'm going to create a function that takes as parameter the original array and the size of the original array and the size of the new array. Okay. Let's create this function. Let's implement it. Take log of a, the size of a, and the size of the new array. As we have seen in the previous video, we have to iterate over all the elements of a and put the result in the array of blocks. On each block, we're going to put the sum of the m cells in the original array. Of course, here we're talking about the sum here, so we have to initialize the new array to 0, all the elements in the new array to 0. Size n, initialize of 0, all the elements here. Okay. So I say return b, not m. Okay. And now let's take it back here. Okay. Look, the array of the square root decomposition technique is built. Now let's query. We're given here, let's take long the sum, call it answer here. Let's create a function that will compute the sum from left to right. It will take as parameter the original array, the array of square root decomposition technique, the size of that array, and of course the left boundary and the right boundary. Okay, array B, and the size of the array B, and the left boundary and the right boundary. While the left boundary is less the right boundary, we're going to test. Check if we are at the beginning of the block, and if we can use the entire block. Yes, use that block, and the answer, I went to the sum here, that's why I make plus here. I wanted to see the addition operator to make the sum. B L over M. Use that block and jump one used, jump to another block. Of course, answer must be initialized to 0. Else, if we cannot use that block, so we're going to use the elements in the array A element by element. So answer, we're going to add to the answer the elements at that position L, and go to the next one. And finally here we're going to return the answer, sum, which is the sum between the left boundary and the right boundary in the original array. I think all is done. Let's check it here. I think it's okay. There is no problem here. I hope so. Let's try to submit. This one. Okay, it's accepted, as you see. Let's go to the second problem. The same second problem here, range XOR queries. The same principle here, the same technique. We're going to use the square root decomposition technique to resolve that problem. The same code, except instead of the plus operator here, we're going to use the XOR operator and the build function and the query function, range query function here, as you see, and here, and here. Let's try it. Let's submit it. This one, I think. Sorry. Okay, it's successful. As you see, this is a typical use of the square root decomposition technique. Maybe later in this lecture, we're going to try to use this technique on a hard problems and see how to, and see the logic behind the solution when you use this technique. In the next video, guys, we're going to use another technique. It's a very cool technique to resolve this kind of problem. See you soon.